Hello folks, in this video I'm gonna just solve questions about non-equilibrium. If you can remember, we talked about equilibrium and non-equilibrium as Newton's applications of Newton's laws, and today we'll be looking at equilibrium examples. This one will be a really short video. I said the same thing in the previous video, it ended up being quite long, but this one I'll be solving several questions as examples, and then that's gonna be it. Just for practicing and helping you understand different situations. So if you can remember, hopefully you watched the previous video, the equilibrium situation was a total force acting on an object or in a system, zero acceleration, zero. Thus, in this situation, the object could be stationary or moving with a constant velocity. So let's do an example. All we're going to use as information is total force is equal to 0 to solve for the equations. And then we have 2D case, we'll be of course looking at total Fx is equal to 0. The total x components of all the forces are equal to 0. And total Fy is equal to 0. And of course, these are also vectors. But slowly we are moving into the phase of jumping from the vectors to magnitudes, as I've taught in the previous lecture video. So we'll be choosing positive, negative directions, define each vector as positive, negative, and then we'll be entering the magnitudes. So example 1 is a nice example. Let me draw it for you. We have a wall in here, a pulley, and a rope is tied to this pulley, and a person is pulling an object with another rope. So he is here, and there is a mass hanging in the center of these two ropes. So mass mg will be pulling down as the force, which is the gravitational force acting on M. Coordinate system is given to us in here. Mass is along y. Positive y direction generally will take general coordinate system directions to be positive and negative in equilibrium questions. And we have forces as tension force T2 in here where the person is pulling, and we have another tension force in here, T1. And the angles are given as, here we have 80-degree angle with y-axis, careful about that, and 10-degree angle with y-axis. So a person is pulling a mass mg with a rope where we have a tension as T2. If the system is in equilibrium, and T1 is equal to 100 Newton, what are the values of mg as Newton and T2 as Newton? This is the question. So a person is pulling a mass, the tension on this rope, T1, is 100 Newton. This one is not working. This is 100 Newton. We don't know the rest of the forces, but we know the arrangement of the forces, we know their angles, so we can solve for the system. We also know the system is in equilibrium. So if the system is in equilibrium, I right away stop and say total Fx is equal to 0 and total Fy is equal to 0. Using this information, I'm going to solve my question. Now I'll have to look at all the components of the forces I have for T1 and T2. Simply, T1 has, sorry, this is T1, this is T2. T1 has a y component, T1y, an x component to the left, T1x, and T2 also has x component to the right, T2x, and y component in downward direction, T2y. One thing to be careful about here again is to find the angles with respect to horizontal axis, x-axis. That's what we used always. You may switch this, but you don't have to if you're not comfortable with this. So always find the angles with respect to x horizontal axis. The angle with horizontal axis for T1 will be 80 degree, for T2 will be 10 degree. Because this whole angle here is a right angle, 90 degree. If we have 10 degree up there, small angle, this will be 80 degree to complete it to 90 degree. Here we have 10 and 80 as well. If this angle is 80, total will be 90 and this angle is 10 degree. So finally what we found is T2 has an angle 10 degree with horizontal axis and T1 has 80 degree. Now let's write down the equilibrium. Total Fx is equal to 0 will give me the total forces to plus direction or to the right will be equal to total forces to the left, because if I write down my total forces, my 2Tx, T2x is positive and T1x is negative. So minus, when I put the magnitudes, I will have T2x minus T1x is equal to 0. And this gives me T1x is equal to T2x. And there I found my T2. Looking at the values, the angle is 80 for T1x. I'll write down T1 cosine 80. And T2x, I'll write down T2 cosine 10. Solving for T2, I will have T2 is equal to T1 cosine 80 divided by cosine 10. Input in T1 value, 100 Newton times cosine 80 divided by cosine 10 will give me the value of T2. And the value we should get from here is .6 Newton. I'm gonna check this. I think it might have a mistake. Let's do this again to make sure it's correct. So 100. Please you also do this so you will learn better and check my answers always. Times, we're all human, we can make mistakes, it's better to check. Cosine 80 divided by cosine 10 will be equal to T2. Yes, 17.6 is the correct answer. Now I got my T2. I'm going to find my weight mg using the equilibrium along y. And what I'm going to be doing is going to be the same. So let me delete that. I hope I had a larger one, so I didn't have to delete everything right after writing. But this is T2, we got that. Let me put it somewhere so we know it now. T2 is equal to 17.6 Newton. Now I'm looking at the equilibrium along y. Total Fy is equal to 0. Up direction is my positive direction, so I have T1y up direction is positive, and downward I have T2y and mg. So I'll be writing T1y minus mg minus T2y is all equal to 0. What I can skip and directly do here is I will be finding the total forces in upward direction will be equal to total forces in downward direction, which comes from here. For example, I'm going to solve for mg. If I let me not leave mg yet. If I just look at this, the total forces upward will be T1y. Take all these negatives to the other side, will be equal to mg plus T2y. You can directly start from here if you like to solve for mg, because the total forces in upward direction will be total forces in downward direction if the system is in equilibrium. But you can also solve with this equation. Positive force minus negative force is equal to 0. Both are the same. I like using this one better because I directly put my forces in one direction equal to forces in the other direction, and then I solve for the force that I want to solve. mg here will be equal to T1y minus T2y. So T1 sine 80 is my T1y, the angle with the horizontal axis is 80, minus T2 sine 10, angle with horizontal axis is 10, will give me my mg value. And if you enter all these values, we got T2 17.6 times sine 10, T1 is 100 times sine 80. You'll find mg as 98.5 Newton. So by setting up a system like this, the person is getting a lot of help using Newton's laws, equilibrium. This rope has 100 Newton tension, and the person is only applying about 18 Newton tension to pull a mass that has about 98.5 Newton tension and weight. It would be very much harder if you just take this weight up with one. It should be, the force you're applying should be equal to 98.5 Newton. But if you set up a system, be clear, smart, and use physics, you'll be applying only 17.6 Newton, or 18 Newton, to raise a mass about 98 Newton. And this is done in real life in construction. People use these kind of systems a lot to take up weights that are a lot heavier than the forces they are using to take them up. So this is one example of equilibrium. Let's solve another example. I'm looking at the time. I'm not going to make this a very large, boring video for you. So let's solve maybe two more examples and then leave it there. I have another example here similar to this one. And we have an airplane in this. This is example 2. This is the bad one. We have an airplane in here fly in this direction. And here as well they give us XY direction. X direction is along the airplane to help us solve the question. And Y direction is perpendicular to the airplane. We'll take this to be positive Y and this to be positive X. Just like on an inclined plane. They show the weight of the airplane as W. And the force that is pushing the airplane to fly by the engine is called T. And there's also an air drag in opposite direction that is called R at the back. And there's also airlift, what is called L. So this figure is given to us by the question. And the question says an airplane flies with a constant speed as shown in figure. The plane has a weight of 86,500 Newton. Let's put in here 86,500 Newton. So we know this value. And its engines provide a forward thrust force T of magnitude 103,000 Newton. Let's put this as well. So T here is equal to 103,000 Newton. We also know this value. In addition, there's a lifting force by air, L, and force R of air resistance are available. Find the values of L and R. So we are trying to find values of L and R. This is almost exactly the same as the previous question. One more value given to us here is that this angle is equal to 30 degrees. We're going to need that to solve our question. So we are trying to find L and R. The system is in equilibrium. If the airplane is flying with a constant velocity, we missed that part. The question says the airplane is flying with a constant velocity. This is important. So acceleration, constant V we have, so the acceleration is 0. So we have equilibrium. Total F is 0. This holds. Total Fx is 0, though total Fy is 0, and that is what I'm going to use to solve this question. Let's start with total Fx is 0. But we're going to need to find the components of the weight. Let's do that first. Show them in here. The weight will have a y component. Let's call this omega y, wy, and an x component to the left, wx. And the angle this weight is making with horizontal axis of choice here, x, is 60 degrees, very similar to the question, the previous question. We have 30 degree here, total degree is 90, so 90 minus 30 will be this angle, 60 degree. So total Fx is 0, will give us forces to the right will be plus, forces to the left will be minus, r is minus, and omega x are minus. So t positive minus omega x minus r are equal to 0. I'll directly jump into the second step. I can say the total forces to the right are equal to total forces to the left, and write down t is equal to omega x plus r. Both gives me the same. And I'm going to solve for r now in here. I know omega, w. I can find wx. And I know t, I can get to r. Solving for r in here, I'll get r is equal to t minus wx. You can use either equation. All gives you the same. T is 103,000 Newton. And wx will be w times cosine 60 as always. And this will give us the value of r. 103,000 Newton, let me put some more, minus 86,500 Newton times cosine 60. And the answer to this question should be, let me find it in here, and please check my answer again to make sure I'm giving you the correct answer, and correct me if I'm wrong. 59,750 Newton. So the air drag on the plane, air resistance on the plane is equal to this value, 59,750 Newton. We got r, we're going to get L in a very similar way as r. We'll be looking at y direction. Our work will be even less. We only have in positive direction L, negative direction omega y, wy, so they will be equal to each other. Let me delete this and put it in here so you can see it better. So this was for fx, it's equal to 0, gave us the value of r. And I'll do the same for y. Total Fy is equal to 0. It will give me positive up direction, so L is positive, minus down direction omega y is equal to 0. Or I directly say forces to one direction, up direction, are equal to forces down direction, so L is equal to wy directly. W sine 60 is the y component always. So L is equal to 86,500 Newton times sine 60. And the answer should be 74,911, around there, 0.2 Newton. And that's it. Equilibrium questions. We look at the forces to one side, and total forces to one side should be equal to total forces to the other side. Along x, horizontal axis, and the same goes for along y. Let me look at one more question, and I'm going to finish this lecture after that. Quite often we will have pulley questions. And the pulley questions, if there's equilibrium, total forces are 0 as always. And another important information is that force along a rope is always the same. We talked about the tension force. So we'll be having tension forces for example 3 pulley questions. And two information, equilibrium, total forces are 0 if the system is in equilibrium. And the tension along the same rope is always the same. Let's start with a simple question. I'll ask you a little bit more complicated one, and then we're done. We're out of here. So we have a mass in here, and a person is pulling this mass on this side. A rope is going around this pulley. We're asked to find the tension force along the rope if the mass is 10 kilograms. If the mass is 10 kilogram, we'll have here mg as the weight. 10 kilogram times 9.8 meters per second squared, so 98 Newton. And we'll divide these systems into pieces to solve it easily, understand it easily. It's very simple, you can see that, I'm sure, but there will be more complicated situations. If I look at this part of the motion, the system is in equilibrium. A is 0, total F is 0, total Fy and total Fy and total Fx are 0. There is no total Fx actually, what we only have is forces along Y. So I have a tension force pulling me up, T, and this tension force is the same along the rope. So if I get it in here, that means I got it in there too. The force pulling up is tension force pulling down is mg. Let's choose our direction of up to be positive, down to be negative. There's no motion, so we can choose either way. If there's motion and total force, then we choose the direction of force to make less mistakes. So total force is up minus total force is down because negative direction, so my mg will be negative. Minus mg is equal to 0, or I can directly jump by say total force is up T equal to total force is down mg. So T is equal to mg, 98 Newton in here. It will be same along the rope, and it will be 98. T is equal to 98 Newton. If I come to this part of the motion, the rope now is pulling down along this stick in here. If I want to find this, let me call this T2, then I show my T as pulling down, and that side is pulling down. So the direction of tension forces along the rope is always in two direction, up and down in here. If you can imagine, if you pull a rope from both sides, you're pulling it, so the tension force in both directions. Depending on which section you're looking at, you'll be choosing your direction. Here, if I'm going to look at this section, I'm going to find the force pulling these up, T2, T will be pulling me down. And the system is in equilibrium as well. The total force is pulling up in this section. If this was asked in the question, it is not. But if this was asked, we can solve for it. Total Fy is equal to 0 gives me total forces in upward direction, T2, is equal to total forces in downward direction, T plus T, so 2 times T. If I'm asked to find T2 pulling up, it would be 2 times T, 2 times 98 Newton. We'll be solving some more complicated questions involving pulleys in the next lecture. But here, let me keep my promise and leave it at this, with these many questions. See you on Monday.